Introduce myself first. I know you know me, but I used to develop technology with the help of people, and a transition happened in my career, and I now develop people who develop technology. So that's the career story of my life. I think it's all about learning, unlearning, relearning. The direction I wanted to take in my career happened, picking the right opportunity, being prepared for that opportunity, and just going ahead and saying, okay, I can do it, I can learn it. If I don't know a topic, I will use my team's strength, team's brain power to learn that topic, and I'm still learning HR, let me admit it. Every day I learn something, both from my team, my peers, and from my manager who's sitting here. So yeah, it's a continuous learning. To see all of you here are so invested in our people that we forget to invest in ourselves. So I think it's a good thing to focus on our learning, sharpen our saw before we take care of others. They say in airplane, please put your seatbelt before you do it for your kid or infant or anybody else. I think learning is just the same. I think we have to invest in ourselves before we take care of others in the organization. So just wanted to share this thought with you. Propel is the initiative which got launched, and this is the first tech talk we are having under that initiative. Thank you, Satish, for taking the mishal forward, let me put it, mashal forward, of learning. And the focus will be, okay, how do we, inspire ourselves and other people to have a learning agility culture or a culture of self-learning. So it starts with me, it starts with us, so let's begin. Over to Satish for introducing the speaker.
Thanks. There's a long achievement list which is there. So Amit is a professor of computer science at IIT Delhi, where he's a faculty since 2003. He's a BTech from IIT Kanpur, Ph.D. from Cornell University. His research lies in the area of combinatorial optimization with emphasis on problems arising in scheduling, graph theory, and clustering. He's a fellow of Indian Academy of Sciences. He got Shanti Swaroop Bhatnagar Award for Mathematical Sciences in 2018. Young Scientist Award in Indian National Science Academy, and Young Engineer Award in Indian National Academy of Engineering, and so on. So let me not just come in the way. So Amit, over to you.
Thank you. Well, thank you so much. So thanks, Satish, and thank you all for coming. Can you hear me till the end? Yes. So thanks for coming on Friday afternoon. I know you must be tired. I promise you I won't show you any equation. I may show you some numbers and some squares and things like that, square roots, but I will not show you any equation. So the talk is high level. I don't assume any background. So, but I hope to convey some of the ideas. I will show you an algorithm, so something which people use, so how it is done. But more than that, the idea is to convey to you what this entire area of clustering is and why it is so important and what are the things going on here. Okay, so what are the main ideas, what are the difficulties, what are the research topics, what are we doing in India here, in our group in IIT Delhi, and so on and so forth. Okay, so feel free to stop me. It's a very sort of general, high level kind of talk. So anytime you feel like asking a question, just stop me. So let's begin. The topic is clustering large data. So there are several terms here. So what I will do is large data we all understand. Large data is any place. We hear this word very often these days because lot of data is generated. You go to Amazon, lot of customers go there. Amazon has lot of data. Google has lot of data. Even a small thing like a network router has lot of data because lot of packets go through it. So, and nowadays we have the capability of just collecting all of this data. So you will see that many organizations or companies or other settings, they have lot of data. And one of the things you want to do is you want to understand this data. And there are many ways of doing it. There's something called machine learning, which is very hot. There's data analysis and those kind of things. But clustering is a sort of a general high level technique which allows you to understand very large amount of data by breaking it into some sort of meaningful clusters. Okay, so for example, you can look at this picture here. The left side picture shows you some dots, and the right side also shows you the same dots but just puts colors on them. So it just puts a little bit of high level meaning to the point, saying that maybe these points are coming from 3 different sources, and what we have done is, just try to group these into three parts. Okay, and that is the high level goal of clustering, that you are given a lot of data, and the first cut is that you just try to cluster this data into some meaningful small number of groups, so that you can try to make a better sort of understanding of the data. As such, it looks very haphazard, but once you cluster them into 3 groups, it's sort of clear as that these are the 3 kind of groups, and maybe this group has this property, this group has this property, and so on and so forth. Okay, so what you want to do is you want to group the data into some sort of meaningful clusters. That's why the name clustering, so that you can have a better understanding of the data. Okay, so let's see some applications before we actually go into the sort of little bit of technical details. So data is sort of given as points. So one thing is that, what is a data? So let's sort of just define what data means here. And for today's talk, what I mean by data is like a point. Okay, so something which has coordinates. So it could be a point, right? And what you want to do is divide the data into meaningful groups. Okay, so what is a point? Point is something which has coordinates. Okay, so you all in high school we read like x coordinate, y coordinate. So that's what I will mean by a data, that something which has coordinates. These coordinates could have different meanings, as we will see. Okay, so this is data lying in 2 coordinates, but you can imagine data lying in 3 coordinates, 3D or 4D or ND or things like that. Now 4D may sound like very strange thing, but as such, just saying that data has 4 coordinates. Okay, nothing else. Okay. So people nowadays even talk about 1,000 dimensions, 10,000 dimensions. All it is saying is that each coordinate is saying something, and you have 10,000 coordinates. Okay, so but that's all it is. It's nothing very sort of fancy. Okay, so let's look at one example. I'll show you many examples. For example, often people use clustering in medical applications. So for example, this is on the x-axis you have blood pressure, on the y-axis you have cholesterol, and these dots are your data points. Okay, so dots represent various people. So a person has some blood pressure and some cholesterol. Okay, and you can think of clustering this also. So if you actually, there is one way of clustering the data points. So one way of grouping the set of people into 2 groups. Okay, and one group could correspond to people who have higher propensity to heart disease, and the other group could be people who have lower propensity to heart disease. So this is one way of understanding data. Then you can say that these are the points, these are the people who it seems have one unique feature, and those are the other set of people who have some other unique feature. So this is one way of understanding people based on just their blood pressure and cholesterol. And why would you want to do that? You would want to do that so that you can understand the nature of these parameters. Now given a new person, you can try to see what is the chances of that person having some sort of heart problem given these data points. So once you understand your data, then you can make predictions about it. Okay, so that's why it's important to do this kind of clustering. Okay, so I want to just divide these points into some sort of meaningful clusters. This is another example. It's again used a lot in genetics. So I won't go into the exact details, but think of the columns are people. Okay, so there are several people. So each of these is a person, and these rows are genes. Okay, and the color is showing some characteristic of that gene. Let's not get into the details, but red means that this gene is expressing something, blue means it is expressing something else, and so on. Okay, and you can kind of see that all of these people, they look similar, and they look different from these kind of people. Okay, so what you have done is you have thought of a person as a data point. Okay, where how does a person look like? A person looks like a column here. Okay. And again, you can see pictorially at least that there are two kind of groups here. What are the two kind of groups? These kind of people is one group, and these kind of people is another group. And these corresponds to different kinds of cancer. Okay. So you can again sort of differentiate between two kinds of cancers based on how how these points corresponding to different people look like. Okay. So again, I have clustered these points. What are the points here? Points are just the columns. So I have clustered these columns here into two kind of groups based on how they look like. Okay. So that's again clustering. Okay. Now given a new person, you can tell which of the two groups that person is likely to belong to, and then can kind of predict which kind of cancer this person has. Okay. Is that okay? Now this is another example in social networks. So this is showing you lots of people, okay, and these lines are telling you who talks to whom, okay, which set of people know each other. And again, you can kind of see groups here. You can kind of see that this is probably one group, this is another group, this is another group, and so on. So again, you can try to cluster these set of people into groups, and the idea would be that each group is is a set of people who know each other well. Okay. So if you have, let's say, again this is interesting. Why is it interesting? Because let's say you're trying to market some product, and you have 5 products that you want to sell, just give it for free to different set of groups. Who will be the people who you would give it to? You won't give it all those 5 products to just one group here. Probably give it to all 5 groups, right? So this way you can kind of understand what are the clusters in your community, so that you can make more intelligent decisions. Okay. So this is again another setting where you are trying to cluster a set of people, entities into meaningful groups. Now one thing I want to point out is that in this example at least, earlier I said that each data is a point which has, what are the coordinates here? Okay. So it turns out that you can always map things to coordinates. For example, here what you can do is, you can represent every person like this as a 1 minus 1 kind of very long vector like this. Why? Because each coordinate is like a person. So this could be me, this could be Satish, this could be someone of you, and so on. And 1 would mean that I know Satish, minus 1 would be that maybe I don't know this person, and so on. Okay. So the number of coordinates here is number of people. We are looking at again dimensions which is 1000, 10,000 depending on how many people there are. And I'll just put a 1 or a minus 1 depending on whether I know this person or I don't know this person. This may look like a very wasteful way of doing things, but turns out it's very useful. Okay. And then once you think of this as a point, then you can try to cluster them. Right. Points which are close to each other, then they're one cluster. Okay. So that's why people often try to map things to points. Why? Because you can check whether 2 points are close to each other or not. You can compute distance between 2 points. How do you compute distance? Well, we know in 2D if these are the 2 points, this is the distance between them. Right? If you know their x coordinate and y coordinate, you can tell what is the distance between 2 points. But this is something I can do in any dimensions, 3 dimensions, 4 dimensions. All I have to know is their coordinates. So that's why people like to think of everything as a coordinate, so that I can check distances between them. Okay. So even though it's not apparent that these are how one can think of these as points, but you can always convert things to points. Okay. And this is another example people use a lot in genetics again, that these are all these species of known to us, and you try to cluster them into groups like this. This is called hierarchical clustering, which means that in the process of evolution, these two were closer to each other than this and this. Okay. So you want to say humans and chimps are closer than humans and horses. So again you're trying to group them in some meaningful groups which looks like this. Okay. So these two are closer than these two are closer to this and to this and so on. Okay. So you're bunching together the species in the manner in which they evolved. Okay. So again it's used a lot in genetics. Many more examples. You can think of customers in Amazon, right? Amazon would like to say that the set of my customers can again be divided into meaningful groups, and so that it can do some targeted ad kind of thing on each of these groups. So again, Amazon would like to understand what are the groups of people, what are the clusters of people who come to me. And again, you can think of a customer as a point. How can you think of a customer as a point? Well, I can think of a customer as a point like this. Okay? Each of these coordinates is a product. Soap, TV, book. And 5 here means that I purchased soap 5 times. 0 means I did not purchase TV from Amazon. 1 means I purchased this book once. Again, so this is a very long sequence, as many as the number of products. Okay, again, it looks like it's a very wasteful way of representing things, because most of the times it will be 0, right? Because I mean, if Amazon is selling 1 million products, I probably would have just bought 100. So, but again, it turns out it's a very useful way of thinking, because it allows you to compute distances between customers, right? If you think of this as a point, then I can say, am I close to you in the Amazon database or not? Right? Are these two customers similar to each other or not? Okay. So of course, Amazon is not going to actually store it like this, but it's going to think of you as like that. Okay. Emails can be clustered. Again, you must have seen that there are automatic ways of grouping emails into groups. This is your office email, this is your home email, and so on. Okay. And how does it do that? Again, it thinks of email as a long coordinate, long list. What are the coordinates here? So the coordinates here would be each possible word. Cell, home, office, each of this is a word. And if it is 2, it says that the word office appears in this email twice. Okay. So again, you can think of an email as a long vector like that. Okay. And again, you can talk about which 2 emails are similar, which 2 are different. So of course, in practice, these are normalized in some ways, but this is one way of thinking about them. So almost any object which you want to think in terms of features, you can think of them as a point. Okay? So people, astronomy people use these things, grouping stars, galaxies, computers, how they are connected, diseases, which 2 diseases are close to each other, drugs, again they try to cluster things. So clustering is an operation which is used almost everywhere in our daily life. Okay? Whenever you want to analyze large amount of data, you would rather first think of grouping them. Okay, so it's a very useful tool for understanding and managing large amount of data. And what you can do is, once you have grouped your data into clusters, then it will allow you to figure out common things, things which are common to each cluster. Okay, so you can say things like a person who buys rice also buys atta, let's say. Okay, so you can make these kind of predictions. And you can also use this to find anomalies in data. Right? These are the people who have high heart disease. They form one cluster. Why is that? So all of them have this common property. So then you can say that maybe this is the reason why they have this anomaly. Okay. So once you cluster, you can also find anomalies in data. Okay. So with that background, I won't show you more examples. I hope I have convinced you that this is a task which is very important. Okay. So the next question which comes is, if I give you a set of points, now you are writing a program which will output some clustering of this. So let's say there is a program which outputs this, okay, and there is another program which outputs this. How do you tell which is the correct clustering, or which is better? Okay, and it may not even be possible to define, say intuitively these things. If you go for a subjective kind of decision, it's not clear whether this is better or this is better. Right? How do you do that? Okay, and note that I am showing you pictures in 2 dimensions. But if these points had 4 coordinates, 5 coordinates, 10 coordinates, then you cannot even visualize these things. How do you say that whatever this program has given is good? Or how does the program even tell that is this good or is this good? Okay, and the only way when you are faced with these kind of decisions is that you assign a numeric value to things. Right? I mean, if you want to compare 2 people, you say that, okay, how many percentage marks did you get and how many you got, and let's see who got higher. Okay, you always find a way of converting things to numbers, because once you convert things to numbers, then you can compare them. Okay, so here also what you want to do is you want to output some sort of number here, right? That the quality of this clustering is 10, the quality of this clustering is 12. 12 is higher than 10 or something, so this is better, something like that. Okay, and that's important because that's how your program will then also use this information to guide itself towards a better solution. Okay, otherwise there is no way your program will know which is better. Okay, so you have to assign a number to each of these, solutions. Each solution is just a grouping, a clustering. Okay, so how do you do that? Well, there are various ways of doing it. There are thousands of definitions, but I will show you the most popular one. Okay, the most popular one goes like this. So let's say you have grouped your data like this. Okay, you have identified 3 clusters here. Okay, then what I will do is I will assign a number to this, how good this clustering is. Okay, and this is called K-means clustering. K refers to how many clusters there are. So K is 3 here in this example. Okay, and what it will do is that it will say that for each cluster you assign some center to that cluster. Okay, so there will be a center to that cluster. So this is the center, that's the center, that's the center. How is that center chosen? I will come to that in a minute. But think of a center as some point which lies in the middle of that cluster. Okay, so for each cluster you also figure out one center. Okay, and then what you do is you look at all these distances. Okay, so distance of every point to the center. Okay, so I just want to make sure that you understand this definition, because everything else will depend on this definition. So I want to spend some time on this. So every cluster you identify a center, and everybody computes the distance to this center. Okay, and you add these things up. Okay, but before adding, you take the sum. For some strange reason, you take the square of these things. So if this was 3, you say it is 9. You take the square of it. If this is 1, it is 1. 1 square is 1. If this is 2, this is 4, and so on. And you add it up for everybody. So it's saying that how far is everybody from the center. And now if you gave me a good clustering, if everybody were tightly together, then this number will be very small. Right? Because everybody is close to the center, then all these distances are very small. And so this entire number will be very small.
Sorry, just one question.
Sure.
This center identification, is it
No,
arbitrary?
no. So center should be chosen in a careful way so that all these. So once I tell you the cluster, once I tell you this group, your center should be chosen such that this sum is minimized. So your center should be really in the center so that this number is as small as possible. I will tell you how to choose the center, but right now just think of it as something really in the center. Okay? Yeah, that's a good question. Yeah, so the question was that what is this center? Is it any arbitrary thing? But it is not. It is chosen in a careful way, in a way so that it lies really in the middle. Okay, just think of it like that right now.
But then the number of data points would also have an impact on the.
Yeah, of course. So if you have more data points, this number will go up. Yes, but think of I am giving you a fixed data point, and with respect to that, you want to find the best clustering, right? Okay, yeah, you're right. So 2 things to remember. One is that you have to figure out the center, and second thing is you have to take the square here. That's important. Okay, this is some very strange reason. You will see, you have to take the square. You cannot just add those numbers. Okay, you have to take the squares. Okay, and just to remind you about distance, how do you calculate distance? This is the formula we all know in high school. This is how you compute distance between 2 points whose coordinates are x1, x2, xd. What is d? D is the dimension. So if d is 2, then you are in 2d. D is 3, you are in 3d. Same formula applies for any dimension. So it's nothing new. Okay, right? Okay, good. So so this is very good, because now this gives me a way of saying which is better. Of course, I have not specified to you how you choose this center, but modulo that, at least we understand that you can assign a number to each clustering, and that's how you can compare two solutions. And it is also intuitive that the smaller it is, the better your solution is. Okay, so so the goal is to find a clustering, group the points so that this number is minimized. Okay, and what does cost mean? Cost is just adding up all of these things. Okay, so now you can compute this thing, and so for every center, for each cluster you define what the center is. You have these numbers after taking their squares and see which one is smaller, and then you can say which one is better. Okay, so this gives you an objective way of saying which clustering is better, and that's important. Okay, one final thing, answering your question about, first of all, why do you even take a square? Why not just add these numbers? The second is, how do you even find the center? Okay, what is the center? Okay. So now let me invert the question and let me say that suppose how should the center look like. So let's say the question is like this, suppose I give you a set of points, okay, and what I want to do is I want to find a center, okay, center could be anywhere, okay, but tell me the center so that if I add up all of these distances, okay, after squaring them it is minimized, okay. So the question you want to really ask is, suppose I give you a set of points, how should you pick the center x such that if I add up all of these distances after squaring them, this is as small as possible. Where does this center should lie? Okay, and you can solve this problem. I will not do it for you. The solution is that that point should be just the average of all of these points. What is the notation? What does this notation mean? The x coordinate of this point will be just add up all the x coordinates of the points and take the average, right. So this center is like the average of all of these points. If you remember something called center of mass in physics, it's the center of mass of these things, okay. Okay, so it's basically saying that if the coordinate x coordinate was 3 here, 5 here, 7 here, 9 here, 10 here, the x coordinate of this thing would be just add up those numbers and take the average, and do the same for y coordinate, do the same for z coordinate and every coordinate. So it's really the average of all of these points, and that makes sense. You take the average of all of the points, it will be something in between, okay. And this is the reason why you take the square also, because if it was not the square, then it is not true that the average is the right center, okay. So the reason why you take a square is that the solution to this problem is the mean, okay. If it were not the square, then solution will not be the mean, it's something complicated, okay. It's because it is a square, that is why the solution is like this, okay. That's the short answer, okay. Fine. So that's why people for some strange reason like to work with squares, okay. I mean intuitively could have put cubes here, 4th power here, anything, but it is square because of just this reason, that if I gave you the set of points, the center should be the mean of those points, the average of those points, okay. All right. So this is called the mean of the points, and this is one thing we will remember. That's why the name K-means comes from, okay. So this problem, remember, is called K-means problem, and this is where the mean word comes from, okay. So this is the most important clustering problem people solve. You may have heard of this, okay. So with that, let me just show you one more slide, okay. So if I told you the center, these are the clusters, then the center, the green center should be the average of each of the clusters, okay. That's the message. So that's how you yeah.
But initially we don't know like how many points would be there in the first cluster, second cluster.
Absolutely. I mean that's the whole non-triviality, but yeah.
That is the problem we are trying to
Yes,
solve.
you are right. So I don't even know what the clusters are, but the whole point here is that if I told you what the clusters are, how would you assign a number to it? How would you tell how good that is? Okay, so don't think about solving the problem. Suppose I showed you a solution, right? So I'm showing you this solution, and I'm asking you how good is that. So this is what it's saying. So you're saying that, look, I will put a center in middle of everything, compute the distances, add them up, and just give a number. And the smaller that number is, the better it is. Yeah, that's all. Okay.
So,
all right.
is it similar to the correlation coefficient, standard deviation that we do in statistics? Standard deviation.
Which definition?
Standard deviation.
Standard deviation. Yeah, it is like standard deviation. You're right, and that's where there also you have a square, if you remember.
Then we have correlation coefficient.
Also, yeah, it's related, but standard deviation typically looks at things in one dimension. Everything is a number. Here you have like coordinates, but it is like standard deviation. And if you remember standard deviation, it is around the mean. That's why the mean comes from here, and that's where the squaring is important. Okay, so okay. Now let me say one more thing. Here you assume that you know k, you know how many. So implicitly, in all of these programs, you have to somehow magically know what is the right value of k. Now sometimes it is obvious. So you are doing spam versus non-spam emails, k is 2. Okay, but sometimes it's not clear. You are just trying to analyze data. You don't know how many clusters you will find. Okay, so how do you know what is the right k? And there is no hard and fast rule here. Typically what people do is they try various values of k. Okay, so they say if k equals 1, what is the cost of the best clustering. And as you increase k, this cost will go down, because the more clusters you put, those distances will start falling down. At some point you will see a kink here in this plot, and so it will tell you that this is the right value of k. Okay, so it's really an engineering thing. Okay, you have to try various values of k and see how this plot looks like. So I will not get into the details of how you figure out what the right k is. So in my talk I will assume that you kind of know what k is, how many clusters you think there should be. If you don't, then you will have to do some sort of analysis like this. Okay, but I will not get into the details of that. But just wanted to say that, you know, even figuring out what is how many clusters the data has is a non-trivial question, but somehow people know this by their domain expertise, or somehow you can figure it out by doing some more analysis. Okay. Okay. Now let me ask you another interesting question, which is the flip side. The flip side is, suppose there was a solution, I did not tell you the solution. Okay, but I told you what the centers were. Okay, so there were 3 clusters. I am not showing you the clusters, but I am showing you the centers. Can you tell me what the clusters were? Okay, and remember again, the reason why you can tell me is that what is the cost of the solution? The cost of the solution is that every point measures the distance to the center, to its center, and you add up all of these things. So which center should it measure to? The nearest one, right? Because you want to minimize this cost. So what that says is that if I told you the centers, the clustering will be automatic. Why? Because every point will say, let's go to the nearest one, right? So this guy will say, I will go here. This guy will say, I will go here. This point will say, I'll go here, and that will show you the clustering. That will give you the clustering. Okay. Right. So if I showed you the centers, you will know what the clustering is. If I showed you the clustering, you will know what the centers are. Okay. So there is this sort of circularity here. Okay. Okay. So I just wanted to appreciate this fact. Okay. So what that says is that there are 2 ways of thinking about clustering. One way of thinking is that you just cluster your data, and the other way of thinking is that you find the centers. Okay, because once you know the centers, you also know the clustering. Okay, so now some bad news. People asked, like, you know, how do you even solve this problem, because it's a chicken and egg problem. If you know the clustering, you know the center. If you know the center, you know the clustering. But how do you even find the best one? Okay, turns out it's a very difficult problem. Okay, even if k equals 2, even if you have to partition your data into 2 clusters, it's an extremely difficult problem. Okay, and the best known algorithms take a lot of time. They take n to the power d. Okay, so if d is like 40, there are 40 dimensions, then this will take forever. You know, it's more than the life of the universe. Okay, so there is no hope of solving this exactly. Okay, so these things cannot be solved exactly. Okay, so what people often do is they, you know, so what that means is that, you know, you cannot say that I have found the best solution. You cannot do that. Okay, there are no ways of doing that. Okay, so what people do is they give heuristics. They give sort of ideas or algorithms which work very well in practice. Okay, and this is the best known heuristic for this. This is the best known algorithm for solving this problem. It's called Lloyd's heuristic. This is the paper which came out with this idea. This paper came out in 1982, and it became so famous that, you know, this algorithm is now called the K-means algorithm. Okay, so when people talk about K-means clustering, often they talk about this algorithm. It's implicit that they are not talking about the problem, but they are talking about this algorithm. Okay, so now what is this algorithm? Okay, I just want to convey this to you, and then okay, so these are the 2 sort of observations we have made. What are the observations? The observations is that if you know what the centers are, then you can tell what the clusters are, and if you know what the clusters are, you can tell what the centers are. Okay, so there is this circularity here. Okay, and this algorithm, what it does is it alternates between these 2 steps. Okay, so let's see how it works. So this is how it works. Suppose this is your data, and you want to divide this into 3 clusters. K equals 3. So it will start by some initial seed of 3 centers. Okay, so let's say it guesses these. Okay, it doesn't know what is the best one, so it just starts with a guess. It says that let me guess that these are the 3 centers. Okay, So once it guesses the centers, what does that do? It also tells me what the clusters should be, right? Because once you know the centers, you know the clusters. So what is the clustering? Everybody goes to the nearest center, right? So this is the clustering, okay? Correct? How did I get this coloring? Everybody is going to the nearest one, okay? So this is the clustering. But if this were the clustering, then what should be the centers? The center should be the means of these clusters. So the center of this cluster cannot be this one. It should be the average of these points. So you update them. Okay? You say that update the centers as average of each of these things. Okay? So this guy moves here, this thing moves here, this thing moves here. Is this point clear? And you just keep on doing this. Okay? So after this, the new centers are like this. But if this is how the centers look like, then you will again update the clustering, and again these centers will move, and they will keep on moving till you have, you reach some sort of termination. Okay. So this is the famous Kmeans algorithm. So should I repeat this? Is this making sense? Is everybody happy with this? Okay. So so the idea is that there is this circularity in the argument, right? If you know centers.
I was just
Sorry.
asking, how do you reach the termination? I was just wondering that how will you decide that, okay, now terminate?
Good question, yeah. And okay, so how do you decide when to stop? Again, the fact is that you define a cost with each solution. What is the cost? Cost is that everybody is measuring how far away I am from the center, and this cost will keep on going down as you make progress. So at some time it will stabilize, it will stop changing, or it won't change much. Then you say let's stop. Okay.
One more issue is gone later than okay.
Sorry.
So I think this red dot in the center, yeah, this red dot
Yeah.
on this side, the center. Yeah, this is quite far from the.
No. So remember, this guy has to decide between whether I go here or here.
Yeah, so isn't it offsetting the other dots?
So no. So this one will just say that this one is closer, so I will color myself red.
So it is affecting the calculation of the next center because it's quite far. Okay.
So no. So this will keep on changing. Sometimes it will be red, sometimes it will be blue,
Yeah.
depending on each time you change the center, this whole thing has to be calculated again, right? So every time you change your centers, you have to calculate what is the new clustering, and then you again calculate what is the new center, and then again you calculate what is the new clustering, and so on. And you just keep on doing this. Okay. At some time you will terminate. You will not terminate, but as some time as you are asking that when should I stop? Well, at some point things will look stable. Okay. I mean.
Iterations that will, the points will not change their clusters. I think that will be the point that you can.
Right. So at some point, yeah. So I mean, it may happen that some small changes keep on happening, right? So it's better to just say that at some point, because what you can prove or can show is that this cost will keep on going down. So at some point it will stabilize. Okay. So it will terminate at some point. Okay. 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 Good. So I have 20 minutes. Okay. So okay. So then good. Great. So this is a great algorithm. It is very popular, used a lot in practice. So what are the next steps? Okay. So so let me show you some of the problems with this. Okay. So first question is, you can ask how fast does it converge? Will it solve my problem in 1 day, 1 hour, 1 second? How fast does it converge? Second question you can ask is, when it converges, how good is the final solution? Is it really giving me what I wanted? Okay. You can ask, what kind of data will it work well? Maybe it doesn't work well always. So what kind of data will it work well? You can ask, can I do something with the data so that it works well on that? Okay. Is that possible? Okay. And all of these questions are very interesting questions. People have studied them for decades. What if data has high dimension, noise, large size? What do you do with these issues? Okay. Okay. So let me give you a quick overview of all of these issues. I won't have time to get into sort of lot of detail, but just want to show you where some of the research directions are. So how fast does it converge? It can take a lot of time. Okay, that's a short answer. On synthetic data, it can take a lot of time. I can synthesize data on which it will take a lot of time. But in practice, on most sufficiently random data, it does fine. Okay, so as such, convergence usually is not a problem. Okay. How good is the final solution? So turns out that it can be pretty bad. Okay, let me show you an example. Suppose forget about these points here. If I didn't show you these points, what are the two clusters of this data? The two clusters is this one and this one. But I claim that this K-means will give you this solution, can give you this solution, where it will group these things into one cluster and these things into one cluster. Why? Why is that? Because suppose these are, if these are your centers, then everybody goes to the closest one. So the upper one here goes here, the lower one here goes here. So then it will say that this is the clustering, right? This is my K-means algorithm. And then how will it update the clustering? It will say that the next set of centers should be the mean of these things, but the average of this thing is exactly this. So it has stabilized, it has converged. Okay, so it can give you a wrong solution. Okay, is this clear? Why? Okay, so it's possible that it gives you a very wrong solution. Okay, and okay, the right solution was that, but it gives you this and this. And why is that? Because you started with two seeds, two initial centers which look like this. Okay.
One question. The data points which we are considering here are discrete in nature, 1, -1 or full numbers. We convert it into linguistic input 0 to 1 range with decimals. Will the result will be?
No. Scaling the data will not make sense.
Scaling.
It is kind of scaling variant. Okay. So what that says is that, okay, so maybe I fooled you, maybe I said that it's unlikely that you will start with these two as your seeds. So you can say that what if the starting two centers you chose were random points? Maybe this will not happen. Maybe there is a sort of an outlier. Maybe in practice this kind of thing will not happen. Okay, because maybe if I had chosen one center here and one center here to begin with, this kind of issue will not arise. Okay, so this algorithm is very sensitive to how you are starting. What is your initial seeding of the centers? Okay, so if you started like this, then there is no hope. It will just converge like this, and it will show you this solution. Okay, and okay, so. And even if you, so this example I will not get into details here, but what you can also give examples where even if you pick these initial seeds, a lot of time when people write programs they say that you have to start with some initial guess. Let me just guess randomly. Okay, just randomly means that you just pick some random point as an initial seed. Okay, but what you can even show that even if you pick random seeds, this can give you very bad sort of result. Okay. So the slide shows that, but let me not go there. Okay. So essentially what you want to do is, what you want to make sure is that the initial seeds that you pick are good. Okay. So that they are close to the so-called right clusters, so that you don't get into this kind of problem. Why was this problem here? Because the initial seeds you picked was, the picture is like this. How do you do that? Okay, so this is where the second idea came. Okay, so this is a paper which came in 2002. It's called Kmeans plus plus, right? So this is the next advancement of this algorithm. Okay, and this was given by two people, Arthur and Wasilewski. Both are at Google Research, and this idea is also very powerful. And each of these is a very simple modification to the initial algorithm. Okay, this idea says that it says something very simple. Okay, so imagine the same sort of setting here. Okay, so there is one cluster, there is another lot of points here, and there is a third cluster. Okay, so these are the three clusters. Okay, and this algorithm, the only modification it makes to the previous algorithm is that it says that how will you choose those initial seeds. Okay, and the choice of the initial seeds should be such that they are very far away from each other. Okay, so it says the following. Okay, let me show you exactly what it says. It says that the first center you pick, just pick a random point. Okay, so let's say you pick this point. Okay, the second seed that you pick should be something which is far from this one. Should be far from this one, so that all the seeds that you pick initially, all the centers that you pick initially are far from each other. How do you do that? Okay, So there is some expression that they give. I will not show you exactly what, but I mean I'll show you how it looks like. But the idea is that the second seed that you pick should be far from this. Okay, so this is the exact algorithm that they give. They say that for the second center, okay, pick the second center with probability which is proportional to distance from this one. Okay, so something which is close to this one has low chance of getting picked, and something which is far from this one has very high chance of getting picked. Okay, and you do this sort of experiment. Okay, so you do some coin tossing, some randomness kind of thing, but you assign a probability to each point. The probability to this point is its distance from this one. So the farther away you are, the higher your chance of getting picked, and you do this experiment. You pick one of them. Okay, fine. So everybody computes the distance to this point. This has high chance, this has low chance, high chance, and so on. And then you pick one point. Let's say you pick this one. How do you pick the third point? Same idea. Something which is close to either this or this will have low chance. Okay, so the third point that you pick will be something which is away from both of these. Okay, so maybe something here. Okay, so that's the initial, so that's the only modification, okay, to k-means. So it just ensures that all the initial seeds that you are picking, they are kind of spread out. They are not all at the same place. Okay, and this very simple modification turns out has lot of nice properties. Okay, in practice it works much better. Okay, and now it is part of all like public implementations. You go to MATLAB or look at any other open source software, all of them will very likely to have k-means plus plus in it. Okay, this plus plus idea. Okay, that the initial seeds are chosen in this manner. Okay, so it also has a name. It's called d-square sampling. But okay, on what data does k-means work well? Okay, so this whole thing that I showed you, when does it work well? And this answer is, the short answer is that the clusters should look spherical and they should be far apart. If your points look like this, then it will work extremely well. Okay, if your points look like that, you know, if you choose those as your initial centers, what it will do? It will cluster them like this. It will say that this is one cluster, this is another cluster. So if your points look like this, it will not work well. Okay, so and this can happen, right? You can sort of, you know, somehow you should be using centimeters here, you used meter here, so everything gets squashed. So the question is, can you sort of, you know, if some directions are more elongated than others, then there are some transformations, as you're saying, that, you know, what you want to do is you want to stretch this dimension so that things look spherical. Okay, and there are automatic ways of doing this. Okay, so I will not go into that, but there are automatic ways of sort of stretching dimensions so that things look spherical. So you may want to do that before you apply k-means. Okay, but what if the clusters look like that? No matter how you stretch them, you know, you cannot make everything spherical. Okay, and in such cases k-means may not give you the right answer. Okay, so if your data looks like this, then you have to use some other things, what is called EM algorithm, but I will not get into that. Okay, so you know, sometimes you may have to worry about the shapes of these clusters. Okay. The other problem with k-means is that it's very sensitive to outliers. Okay, what does outlier mean? Suppose your data looks like this, okay, but there is one wrong measurement. That spurious measurement shouldn't have been there, but just somehow got in there. Okay, now what is your answer? Suppose you want to break your data into two clusters. How should the answer look like? This is one cluster, this is another cluster. That's how the answer should look like, right? So that's how it should look like. And what about this guy? It will go into one of the two. Doesn't matter, right? It's anyway a bogus point. Okay, but you see what has happened. The way we measure the quality of our solution is you compute this number. So what will this number look like? So the center of this blue cluster will be somewhere here because there are a lot of points here, and then you will take this long thing, right? You will take the square of that. So everything here was close to 0, but this is 100. The cost of the solution is 100 square. Okay, and if you run your k-means algorithm, this k-means algorithm, you know what it will do? It will show you this answer, that all of this is one cluster and this is the second cluster, because this has much smaller cost. So the moment you throw in this noise, it sort of starts behaving randomly. Okay, it's very noise. Okay, you want to do something so that you remove all of those kind of things before you run your k-means. Okay, Otherwise, it can give you completely wrong answers. Okay. So the way to fix is you either fix the solution, that's what people do, fix the algorithm, you make some tweaks in the K-means algorithm so that it first identifies those things, removes them and then runs it. Or you say that I will not take the square, because square kind of amplifies the problem. If this was 10, if you take the square, it becomes 100. Okay, so you do something else. Okay, so again, this is a whole area of research. I will not get into, let me not get into all this. Okay. So let me just talk a little bit about our research group here and what are the kind of questions we are asking. So these are the current set of people. Ragesh is a faculty member, they are PhD students, and we sort of look at these kind of issues. Okay, so just wanted to just mention towards the end 3-4 problems that we have been looking at. Okay, and just give you a sense of where is the research going here. So one question people ask is, can we even do better than K-means plus plus? Let's say I have lot of processing power, clusters, computers. Can I do better? GPUs, can I do better? Right? Or is K-means plus plus the final answer? Right? So can I give solutions which are even better than K-means plus plus? Okay. Turns out that there is. Okay. So what you do is, remember this K-means algorithm, it picks some initial K seeds. So what you do is you pick a larger set of seeds initially, and then do some heavy processing, and that crystallizes to you some even better set of initial seeds. Okay, and then you do that. Okay, so turns out this code can be parallelized. You can run it on GPUs, on multiple processors, and often it will give you better results than just K-means plus plus. Okay, so that's one direction that people are looking at. Other is, people often want to understand data, that under what conditions. And I mentioned this earlier also, will K-means plus plus work well? Okay, and if I can say this precisely, then I can test this on my data and say that yeah, this data has this property, so then I can apply K-means plus plus to it. Right? Otherwise, I have no way of saying. Okay, so are these conditions realistic? Can we test them on real data and say that look, this is the data on which you want to run K-means? Yes, it satisfies these test conditions. So this will my method will work well. This K-means plus plus will work well. Okay. Sometimes you want to get into what is called semi-supervised setting. Sometimes what you want is that there is a human person who can give feedback. Right. So you can ask questions like, are these two customers similar or not? Right. Do you think these two people have the same disease? But of course, you can ask only a limited number of such questions. Can this help? Can this help my algorithm? Can I get dramatically better results? Okay, by asking a few questions to some expert. Okay. This is another very big issue these days, fairness. Right? I want to group these set of people into two groups, criminals and non-criminals. But I want to ensure that they are gender neutral, right? Or race neutral, or religion neutral. Okay. So I want my clustering to have some certain extra properties. Right? They have equal number of males and females, equal number of people of various religion, things like that. Okay. So what if I impose such conditions on my solution, that it should also have these fairness kind of criteria? Can I now modify my all these algorithms to have these kind of properties? How do they work in practice? Okay. So again, these are very important questions, and we are working on many of these settings. Okay. So if you want to know more, you can go to our website and just see. Okay, so let me just conclude the final slide, that clustering is a fundamental tool which is used to understand data. It's very widely used, and many challenges remain in designing the right algorithms and also in understanding the settings where you should be applying these algorithms. And domain experience is also a very important aspect here. Okay. All right, thank you.
One question. So apart from this algorithm, are there separate genre of algorithms also which kind of compete in this space, or this is?
People have proposed all kinds of algorithms. Okay, so if you go to literature, you will see dozens of algorithms, but this remains the most widely used.
Okay. Yeah. So for clustering the documents, like where the documents are large, containing large amount of data, especially the text stuff. So is it okay to use K-means, because like we have used it and the results are not so good.
So in which setting, when you have lot of coordinates?
Yeah, lot of words are there. Actually, words are the features in the textual data.
Right.
So it's a high dimensional data.
Right.
And it's a text.
High dimensionality brings lot of issues. Okay, it brings with it lot of issues, and I didn't show those slides. We are out of time, but essentially what you want to do is what people often call it spectral clustering. So what you want to do is, when your data has lot of high dimensions, it's likely that it also has lot of noise. Okay, and as I showed you that if you have noise, then these things can work very poorly. So what you often want to do is, you want to sort of, let's say the number of dimensions is 1000. Okay, so sometimes what people do is they reduce the number of dimensions to maybe 10. Okay, how do they do that? There are ways of figuring out what are the right 10 dimensions. Okay, which are the right 10 dimensions. So they will reduce it to 10 dimensions and then run K-means on it. And often what that does is, it kind of removes these kind of noise. So whenever you are working with high dimensions, all of these issues will come in. Also, a lot of data engineering is needed. You may want to just normalize your data. So for example, the one I showed for emails, that's not how it is used as it is. Okay, so for example, why? Because, for example, the word "the" appears in every email, and it will appear in every email the most number of times, and that will really confuse the algorithm. That it's all "the," right? "The" dominates everything else. So you want to lower down the emphasis of "the." So people have these kind of normalization techniques where they take care of these issues. So you may want to just normalize your data, and then you also have to look at reducing the number of dimensions. So that's called spectral clustering, which I didn't talk about.
One question: can this be used as a approximation method to train the model in supervised learning? Is it
to do what?
To do approximation in supervised learning to train our data model.
Supervised learning is something else, right? In supervised learning, you are already giving the sort of solution.
Yes. So data minimum technique is also used there, where we are doing the average to identify the delta between the target model and the current input. So I just want to get maybe your experience. You can tell if this technique can also be used in supervised learning or not.
Typically, it is not used in supervised learning, because supervised you already have a lot of information about the clusters. Yeah.
One question. In relation to that particular algorithm which talks about finding the initial seeds, let's say we have n data points and we have 3 dimensions. So can we take the maximum and minimum of those data points and find the equidistance data between those as per the dimensions, take them as the initial seeds?
Yeah, so what you're saying is that why do all this random probabilistic thing, just pick 2 very far away points.
Not too far away, but let's say we need to decide 3 Ks, okay, 3 clusters. If we decide that we need to find out 3 clusters, so we need to find out 3 centers. And to find out those 3 centers, can you pick the minimum from that data point and the maximum, and then find the 3 points between them?
So so people have tried many of these heuristics, okay, and somehow it may seem strange, why do we even need this probability kind of thing, right, randomness, but somehow it, both in the formal mathematics and in practice, it turns out it's very useful. Okay, I cannot explain more to that. Okay, somehow this is the feature about randomness. Somehow adding randomness does not fix you to one rule, and that always helps. Right, often you would have seen that let's do something randomly, choose some initial number randomly, and this randomness is important. Okay, it's not just like a wasteful thing. But here all people are saying is that, okay, we will still use the randomness, but we'll add some more tweaks to it. You still want to have that randomness in it in your algorithm.
Thank you, Amit, for
Thank you so much.
Wonderful small Thank you. I think it's been, obviously, as I said in the beginning, I don't know how much of technical I will understand, but definitely I think what was really interesting was the social network example which you gave, because a couple of months back I had a HR consultant and we were talking to him about why change management programs in companies fail. And most of the change management programs, you always start with a hierarchical structure in the company. And that's where he gave actually this example to me that in an organization, you have to really look for the informal networks which exist. And the way you can find out, obviously, who's sending mails to whom, who's meeting whom at the tea shop or the coffee shop. Or, so obviously you have to get maybe the data dimensions, many ones, and then map it, possibly do this kind of clustering, find which are the groups, and then maybe go to those groups and try to sell them. So it's interesting from that perspective. But thanks, I think this is an interesting, thanks Satish for organizing this, because we need to do many more of this. And I know, I think your schedule is very busy. You're traveling to the US next week, but could take out time. Because sometimes I think we have to go back to also to the theoretical aspect to see how it can be brought back. So I'm sure this will also encourage people to go back and study algorithms or papers, some of them which you were mentioning. And thank you once again for being with us.
Thank you for
very
inviting
much.
us. Thank you.